Let us move on to another important topic, that is the sp mixing. What is sp mixing? Sp mixing is nothing but the 2s and 2pz orbitals which are having same symmetry and comparable energy actually mixed together. This is more pronounced in diatomic molecules of second row elements, mainly lithium, beryllium, boron, carbon and nitrogen. Due to 2s 2p mixing, the pi orbitals, if you look here, the pi 2p orbitals, the bonding orbitals are lowered in energy compared to the sigma 2p bonding orbitals. So this is what is called sp mixing. In the case of oxygen, fluorine and neon, the energy difference between the 2s and 2p orbitals are relatively higher. So there is no s and p orbital mixing takes place here. If you look at the energy difference between 2p and 2s, this delta E is comparatively smaller with respect to the delta E difference between 2p orbitals and 2s orbitals of oxygen, fluorine and neon. So since these two this s orbitals and p orbitals lie close or comparable in energy, there is a overlap between s and p, so that is what is called sp mixing. Let us look at the reason behind why the sp mixing changes the order of molecular orbitals. This is basically based on the energy of the interacting atomic orbitals. From lithium to nitrogen, there is relatively small energy difference between the s and p orbitals. To form each atoms from lithium to nitrogen, there is relatively small energy difference between the 2s and 2p atomic orbital. One 2s atomic orbital from each atom and one 2p atomic orbital from each atom combined to give 2 sigma bonds or 4 molecular orbitals, 2 bonding and 2 antibonding orbitals. So the sigma bond formed by the 2s atomic orbital mixing is lowered in energy. To compensate the lowering of the energy, the other sigma bond formed by the 2p atomic orbitals are raised in energy. So when these two mixing happens, what happens is this 2s and 2s combine and their energy is actually lowered. So to compensate the lowering of this energy, the 2p mixing to give the sigma orbital is raised in energy. So this is how the lowering of 2s orbital's energy and the hiring of sigma 2p orbital happens. This puts the pi bond, that is the bonding orbitals, in between the sigma 2p and the sigma star 2s antibonding orbitals. So when we look at the sp mixing, the major thing what you have to understand is the sigma 2s orbitals are lowered in energy and sigma 2p orbitals are raised in energy because s and p orbitals are having comparable energy. So that leads to reordering of the energy of various orbitals. In the case of oxygen, fluorine or neon, the 2s orbital is actually having the energy difference between the 2s orbital and 2p orbital are little bit higher. So that is the reason there is no mixing between 2s and the 2p orbital takes place. So when there is no mixing, the 2s orbital combine to form separately the sigma 2s and sigma star 2s orbitals, and the 2p actually gives sigma 2p, pi 2p, pi star 2p and sigma star 2p. So these orbitals are formed as the normal case. So between the sp mixing and the sp no mixing, we can actually say the comparable energy and the same symmetry is responsible for this phenomenon. So when we look at the energy levels of the molecular orbitals, the order of filling without 2s 2p mixing is basically the first orbital, the lowest one is the bonding 1s orbital, sigma bonding 1s orbital, followed by sigma star 1s, that is anti-bonding orbital. Then comes the sigma 2s orbital, sigma star 2s orbital, and the next one obviously going to be the sigma 2p orbital, then pi 2p orbital, pi star 2p antibonding orbital, and sigma star 2p antibonding orbital. So this is the normal order of filling when there is no sp mixing. But when there is a sp mixing, what happens is the lower 1s orbitals are no change is happening here. In the case of 2s orbital also there is no change happening. So the sigma bonding and antibonding orbitals are lower in energy. The only difference happens is in the pi orbital and the sigma orbital. So the pi 2p orbital is having lower energy, whereas sigma 2p orbital is having higher energy. So this is the only difference, which is called the sp mixing. Here is the overall MO diagram of various second row elements. For boron, carbon and nitrogen, we have 2p mixing. For oxygen and fluorine, there is no 2p mixing. So if we look at the normal order, it is basically 2s sigma 2s, that is bonding orbital, sigma star 2s anti-bonding orbital, then it should be sigma 2p orbital, that is the normal case. But because of the sp mixing, what happens is these are the order actually changes as shown here. When we look at the bond order of B2, it has 2 electrons in the 2p pi bonding molecular orbital. So its bond order is basically 1. For C2, there are 4 electrons in the 2p pi bonding molecular orbitals. So its bond order is 2. In the case of nitrogen, 6 electrons are present in the 2p sigma and pi bonding molecular orbitals. Its bond order is 3. So that is how we can actually explain the different bonding patterns in B2, C2 and N2. For oxygen, 6 electrons are in the 2p sigma and pi bonding molecular orbitals and 2 electrons in the 2p pi star antibonding orbitals. So here we have 2 electrons in the antibonding orbitals. So its bond order is basically 2. Because of the presence of this unpaired electrons in the antibonding orbitals, we say oxygen is paramagnetic. And the MO theory successfully explained the observed paramagnetic character or the nature of oxygen. And when we move on to the fluorine, we actually have a diamagnetic because these electrons are paired in the antibonding and bonding orbital also. All the electrons are paired, so we have a diamagnetic F2 molecule. And since 2 electrons are kept in the antibonding orbital, we can also explain the triplet ground state in the case of oxygen. Let us move on to the heteronuclear diatomic molecule. So far we had seen homonuclear diatomic molecule. So there were no electronegativity difference between the atoms. Now we are moving on to a new set of compounds. Here we have different atoms having different energy of atomic orbitals. Here the orbital interactions are dependent on the electronegativity of the element. So this is the most important thing. We are moving from the homonuclear to heteronuclear diatomic molecules. We will be studying about HCl, HF, NO and CO. Before we delve into the molecular orbital theory for these HCl, HF and other heteroatomic molecules, let us look at ionization energies of atomic orbitals. Basically, this is expressed in terms of electron volt as given in this table. When we allow atomic orbital to interact, for effective molecular orbital formation, they need to have comparable energies. So, let us say if we are going to form a HF molecule, the hydrogen's 1s orbital and the pz orbital of fluorine are little bit different in energy. So that means if we have to form a effective overlap, hydrogen having 1s orbital's energy approximately 13.6 can actually form a very good 2p orbital from the nitrogen, which is having 13.1 electron volt. So in other words, nitrogen and hydrogen can form a very good overlap. Whereas when we go to the fluorine, the energy difference is little bit higher, so that means the effective overlap is going to be very difficult.